Hello everyone. Today we're gonna talk about evaluating the impact of New York City's congestion pricing on air quality. Next page. So here's our contents. Next. And let's start from background and significance. Next. Here's some basic knowledge about New York congestion pricing, and the goal of this policy is to reduce traffic congestion and improve air quality. And we're gonna focus on improve air quality this objective to quantify policy impact on PM 2.5. Next.
So here we come to the problem statement. Next page. So our research aims to evaluate the impact of New York's congestion pricing policy on air quality. So first, we hypothesize that the implementation of congestion pricing has led to a reduction in traffic volume in New York. So based on data from the NTA, we can see the average commuting time within the toll zone south of 60th Street has decreased compared to the same period of last year. And next page. Second, we hypothesize that the reduction in traffic volume contributes to a decline in PM 2.5 concentration. So, parallel to New York, London has implemented a similar road pricing scheme and reported significant improvement in air quality. However, due to a limitation in traffic data timeliness, our analysis does not test the full causal chain. Instead, we focus on the correlation between the policy and air quality outcomes. Next page.
Let's move on to model selection and data resources. We selected a linear regression model to predict PM2.5 levels in 2025. This choice was driven by the nature of our input features, which include 3 lag turns, 1 hour, 24-hour, and 1 week lags, along with 2 rolling average turns over 3 and 12 hours. Additionally, we incorporated temporal features like a binary weekend indicator, annual seasonality using sine and cosine turns, and a policy time indicator starting from May 1st, 2025. We sourced data from multiple reliable channels to ensure comprehensive coverage, air quality data from the NYC Department of Health and Mental Hygiene, traffic-related data from MTA hourly traffic records and OpenNYC. We also incorporated congestion zone vehicle entries data. Let's move on to data visualization and interpretation. Here we evaluate the performance of our linear regression model for predicting PM2.5 concentrations in downtown NYC. The scatter plot on the left shows actual versus predicted PM2.5 levels, with most points clustering tightly around the y=2x line, indicating a strong fit. On the right, we compare model metrics between the 2024 validation set and 2025 predictions. The R-square values are rather close to 1, reflecting excellent power. The MSE is low, confirming high prediction accuracy. However, we observe some outliers with larger residuals, suggesting a need for specialized peak level modeling. In this section, we evaluate the air quality impact of CP in downtown NYC by comparing our baseline model's predictions trained on pre-CP data with actual PM2.5 levels. In the top plot, green bars represent days where the baseline model predicted higher PM2.5 levels than observed, indicating that CP likely reduced pollution. Orange bars show days where we observe PM2.5 exceeded predictions, such as mid-January, mid-February, and mid-April, likely due to adverse weather or emission spikes. While most days show green bars showing a net PM2.5 reduction. The bottom plot illustrates the cumulative effect of CP on PM2.5 levels. Starting at 0 in early January, the blue line rises steadily, reaching approximately 7 microgram per cubic meter by the end of April. The solid green fill indicates days where the baseline forecast exceeded actual PM2.5 levels, meaning the policy effectively reduced pollution. The upward-only trend, with no red shading, highlights 2 key findings: an overall improvement and a consistent effect.
In this section, we estimate an ordinary least square model using hourly PM 2.5 concentrations from generation 1, 2020 to December 31, 2024. The model includes weather control variables, annual sign, and the cost terms to capture seasonal trends, a weekend indicator, lagging PM 2.5 values at 124 and 168-hour intervals, as well as 3-hour and 12-hour rolling averages. Model performance is evaluated by time series split cross validation method, yielding an R square of approximately 0.92 and a mean squared error of around 1.05. We then re-estimate the model using data through the end of 2024 and forecast PM 2.5 levels for January to April 2025 under a counterfactual scenario in which the policy variables is set to 0. For the table, we can read that the policy parameters keep small, although there is a normalization multiplier. So it seems like the policy has less influences on the PM 2.5. We also do confidence checking about the outcome. Although the forecast residues are minimal, statistical inference based on confidence interval testing reveals that the estimated impact is not significant at the 95% confidence level. Consequently, the effect of congestion pricing on air quality in Midtown appears to be limited. Next, please.
We also use the ID test to test if there are true casual effect of a congestion pricing policy on the air quality. There are two groups in the DID test. One is control group, another one is a treatment group. In our case, we use Bronx as a control group, since Bronx is not in the congestion pricing zone, and compared with the Midtown and downtown Manhattan. Next page. So let's move on to the details of the model. This is the equation we used. You can see four beta value here. The beta 0 is the baseline PM 2.5 level. That is the average pollution in the control group before policy. Beta 1 captures the general time trend, how pollution change over time in every group, even without the policy. The beta 2 reflects the baseline difference between the treatment group and the control group. Basically, it answers which one is more polluted, even before the policy. The key part is the beta 3. This is our DID term. This tells how much more or less pollution changes in the treated area compared to the control group after the policy is implemented. If the beta 3 is negative and significant, this means the policy had a real impact and actually helped reduce air pollution beyond we would expect from the general trend. And finally, the last term is the error term. Next page.
So now we can talk about the detailed analysis of our part. So first we compare downtown as the treatment group with the Bronx as the control group. And first, the policy coefficient is -2, indicating a general decrease of 2 microgram per cubic meter in PM 2.5 across New York City during the policy period. And this drop may reflect broader external factors like seasonal changes. And then we move on to the group coefficient, which measures baseline differences between downtown and the Bronx before the policy. So we can see that it's actually insignificant, which suggests that both areas have similar air quality prior to the intervention. And third, the intervention term between time and treatment group is actually -0.586, which is highly significant. So it means that after accounting for general trends and baseline differences, PM 2.5 levels in downtown declined by an additional 0.59 microgram per cubic meter compared to the Bronx, which is evidence of a clear policy effect. So together, all these findings suggest that the CP policy had led to a measurable and targeted impact on improving the air quality within the charged zone. And next page. So let's move on to the Midtown, compare with the Bronx. So here in the second part of our analysis, starting with the policy coefficient, we can see that still a value of -2, which is the same as we mentioned before, and indicating a general citywide drop of 2 microgram per cubic meter in PM 2.5 levels. And next, the group coefficient is actually insignificant, which also suggests the two regions had comparable PM 2.5 levels before the policy. And third, it's about the interaction term, which is like -0.316, and it is actually statistically significant at the 5% level. So this implies that the PM2.5 concentration in Midtown decreased by an additional 0.32 microgram per cubic meter relative to the Bronx after the CP policy, and also demonstrating a localized policy effect. So as seen in the slow plot, both areas show post-policy declines, but the reduction is more pronounced in Midtown. And although the effect is actually smaller than downtown, it remains meaningful, suggesting that CP policy has contributed to air quality improvement across multiple urban centers. And however, the comparison between the Bronx and Midtown yields different results from our research and the previous linear regression. So this primarily due to the methodology differences. So here we adopt the results from the more accurate linear regression as the benchmark. Next page.
From our results, we aggregate our outcome and make some policy advice. We can see that only the Manhattan Financial District shown better air quality than what our baseline prediction estimated. This outcome aligns with our earlier hypothesis. It appears that the congestion pricing policy had the strongest impact specifically in the Manhattan Financial District. This could be due to what we call the localized effect. In other words, the policy seems to reduce traffic volume more effectively in the specific area compared to others. Another way to understand this is through the nature of PM2.5 itself. PM2.5 is a form of lying particulate matter suspended in the air, and its concentration often depends heavily on local conditions. This helps explain why even in other areas where congestion pricing was implemented, the reduction in PM2.5 level was not as significant or varied much less. The Bronx, in particular, serves as a very clear control group. There we saw almost no extra change in the air quality compared to previous levels. There was only the seasonal change, which was not contained into the policy making. This contrast strongly supports that the policy success in Manhattan Financial District was both real and localized. Next page, please. About the policy suggestion based on our findings. First, to achieve a positive environmental effect, we recommended considering policies such as congestion pricing. As shown in our results, this type of policy can significantly reduce air pollution, especially in high traffic areas. However, just implementing the policy is not enough. It is also important to apply it with more accuracy, targeting the core issues and focusing on the areas where it's likely to make the most impact. The more data-driven and localized approach would likely improve its effectiveness. Next, in terms of elevating traffic congestion, our data show that the congestion pricing has already had a positive effect. Eventually, the time-specific pricing measure proved to be both effective and precious in controlling traffic flow. This strategy works by discouraging vehicle use during peak hours, which helps to reduce road volume and improve traffic conditions. In summary, congestion pricing, when well targeted and well timed, not only contributes to clean area, but also helps in managing urban traffic more efficiently. Next, please.
Okay, this part we talk about the limitation and future improvements. Next. In this slide, we summarize the main limitations of our current analysis. First, the use of linear regression models impose simplified assumptions about the relationship between variables, potentially missing important nonlinear intersection. Second, the policy time variable is treated as a binary step function. This doesn't capture the gradual behavior changes that likely occur after the implementation of congestion pricing. Lastly, our analysis focused only on the short-term response immediately after the policy took effect. Next. Here we propose several directions for future improvements. First, to better model real-world complexity, we can incorporate nonlinear models, such as tree-based, to capture intersection between features. Second, the policy variable design could be improved. Instead of a binary switch, we could use the continuous or multi-level indicators to represent different phases or intensities of policy implementation. Lastly, expanding the model to include additional pollutions and weather variables would enable a more holistic understanding of air quality dynamics and policy impact. Next. Here's the contributions of our teamwork. Next. Here's the reference. Thanks all.